Here comes that Unit 3 practice test. Try to talk through it and see why I think the answers are the way they are. Maybe drawing a few little diagrams along the way, like some heating and cooling curves. I may even be able to switch from here or here. All right, see what I got available. When a sample of liquid is cooled, okay, it's liquid and it's cooling. So what's happening to its phase energy? Here's a cooling curve. When a liquid is cooled, its phase energy isn't doing anything. It's staying the same. I would say remains the same. While a sample of a liquid is evaporating, let's go to where, let's see, we must be adding heat. Here's a heating curve. The evaporation part happens here. Evaporation. What's happening there? Well, one kind of energy, the phase energy, is changing, but the thermal energy is staying the same. While a sample of liquid is evaporating, its thermal energy remains the same. So there's that misconception that, of course, if you add heat, it's going to heat up. But in this case, it doesn't. It does one or the other. It's either going to be changing phase or it's going to be changing temperature, but it doesn't do both at the same time for some strange reason. The graph at right represents the temp time behavior. What was initially a sample of ice. Let's say it's ice down there. At 0 degrees Celsius, use the following questions for answers 3 to 5, or the following choices. During region B, the phase energy, that's right here. Well, it's changing temp, so its phase energy is the same. It's letter C, or the same. C. During region C, the phase energy, however, is changing. How is it changing? Well, we're adding energy, so in C, it is, let's see, it's changing from a liquid to a gas. That's going to be 2 more bars of energy to make it jump out of the container. We're going to say that it's increasing. Letter A. During region A, the thermal energy is, this is a tough call. The way they drew this thing, they actually show little tiny, I don't like the way, I didn't design this test. We generally show straight little plateaus and we assume there is no temperature change. I think what they were going for is the same. The thermal energy is C, the same. But the problem is, the way that that's showing, you could say a little tiny bit it's increasing and decreasing, but it doesn't give that choice. The same is going to be my best answer. During region C of the graph, the energy being absorbed is, let's see, what is the energy doing? Here, letter C, sure isn't making it warmer, otherwise the temperature would be up there. All the plateaus are simply, well, it's evaporating or vaporizing. We can call it a couple of different things. So let's see what that says. During region C, the energy being absorbed is it increasing the velocity of the, ooh, I like this. When they talk about the velocity, that's speed, and speed is temp. There is no change in temp. Is it increasing the distance between the water particles and reducing their phase energy? I believe it is making them further apart, increasing the distance. But wait, when you increase their distance, that doesn't reduce their phase energy, that's adding it. B is not good. Is it increasing the distance between the water particles? Yep, we just established that. It's making them further apart. It's also increasing their phase energy. I'm thinking we have a winner. Is it decreasing the velocity? Well, if that's going to be slow down, and that would be, so I was pretty sure C was my correct answer, but I checked D just to see. Slow down means less temp. Nope, there's no temp change. Best answer there will be C. During region B of the graph on the previous page, the energy being absorbed is region B. Okay, let me go back. And what is the energy doing? Region B on the graph. Let me just see if I can put this on the page that I need it. We can just put it right down here for now. We'll get rid of it in a little bit. During region B, the energy being absorbed, is it increasing the velocity of the water particles? What does it mean to increase the velocity? It means to make them go faster. And when they go faster, that's directly affects, that's just an indication of temp. I believe that A is the best answer, but there's no way I'm going to put it and move on. Is it going to increase the distance between the water particles and reduce their phase energy? There is no phase change at letter B. It is simply changing in temperature, so no, it's not going to reduce their phase energy. Increasing the distance between the water particles and increasing their phase energy. No change in phase energy. Is it decreasing the velocity? That would be colder. Yeah, I was right. A. Maybe I should have just went with it. We don't need this anymore. We'll shove this up out of the way. 8. A sample of water in a pan is brought to a boil. Which of the following is true when boiling occurs? The temperature of the boiling water gradually increases. Wait a minute. So you got to think this through. They didn't say as it's brought from room temperature up to boiling. They're saying when boiling occurs. And what we found is we kept cooking and cooking and cooking. It stayed just about 100 degrees Celsius. I do not think that it gradually increases. It stays the same. It did to get there, but the question says when boiling occurs. The liquid water immediately flashes into gaseous water. Immediate? Nah, it's kind of a gradual process with lots of bubbles. I'm saying no. I'm saying no. The temperature of the boiling water remains constant. I think we have a winner. The liquid water begins to break down and now never mentioned. I guess we don't have a lot of information to know that that isn't the case, but never mentioned. C is the best answer. Sample of water is brought to a boil. Inside a bubble. What's in there? What's inside the bubble? Well, what we're doing is we're changing something. We're changing a substance. That substance is good old H2O. And we are changing it. Well, we're not changing it into a new substance. We're not destroying its integrity. Nothing of that's been mentioned. We're simply changing its phase. So what's in there? Particles of water. When liquid water is boiled into steam, does the water absorb energy from the surroundings? Well, it's got to get that energy from somewhere, and even the Bunsen burner. I'm liking that so far. The water releases energy to the surroundings. If it released it, it would cool off. The water particles are arranged in an orderly pattern. No, that would be a solid, and we're already way up into where they're bouncing around and bouncing off the ceiling. H2O particles split. They keep hinting at this idea that particles can split, but nothing has been discussed of that. A is our best answer. Energy bar charts. For each of the situations, use an energy bar chart to represent the ways that energy is stored in the system. Hey, here's our friend, dry ice. Dry ice is made of CO2. If you simply wrote dry ice here, it's because what should we write in there? That's the system. That's the stuff that we're going to be focusing on. Not the counter that it's sitting on or the room that it's in, but the dry ice or the CO2 itself. A piece of dry ice sublimates. What do we know about dry ice? It's a solid, meaning it's got, let's see, I should have a line right there. It has 2 bars of phase energy. What do we know about dry ice? It's pretty darn cold. I don't like half bars though, so I'm just going to say 1 bar, but half would certainly be a good indication. A piece of dry ice sublimates. Okay, it was really cold and it's going to be at room temperature. It means that it's going to get warmer. You know what that takes? Well, let's just figure it out. When it sublimates, hopefully you had that look up. Sublimate is the process of changing from a solid directly into a gas with no intermediate liquid phase. So it's going from solid. Did that wrong, didn't I? I got to back up. I'm fixing this. Yep, 2 bars was wrong. It was a solid, so it's only 1 bar. But now it's somehow a gas, and that's going to be EPH. That's going to be 1, 2, 3, 4 bars. So sorry about that. Not going to go back and redo it. Room temperature, certainly much colder or much warmer than dry ice. I can call it 2 bars. I can call it 3 bars, but it's so, I'm just going to say 3. It doesn't really matter. If I have 2 bars turning into 4 plus 3 is 7 bars, whoa, I got to gain a lot of energy. 1, 2, 3, 4 lines make 5 bars. Best way to make sure that if I see this like this, just take the guesswork out of it and write down things like, even though it doesn't say so in the directions, write down how many bars and how many. 5 bars have to go into melting that, turns it into a gas at room temperature. Tray of ice at -8 sits on a counter until it's room temperature. Let me kind of bring this up to EPH, ECH, even though we don't need all that. Okay. Tray of ice. 1 bar. -8, pretty darn cold, 1 bar. Sits on the counter. Ice or water is my system. It's going to melt and even warm up some more. So it was ice at -8. It's got to warm up a little, melt a little, and warm up some more. So when it's all done, it's a liquid. It only has 2 bars of phase. But it's going to be quite a bit warmer. I'm going to say maybe a 3. You could have said 2. It would have been fine. If 2 changes into 5 bars, that means that we had to add 1, 2 lines to make 3 bars. I like my arrows to make sure that I'm showing which direction that it's going into. You add heat to make it warm up. You take away heat to make it cool off. Temp time graphs for each of the situations below. Sketch the temp time graph. Be sure to include the beginning and ending temps, as well as the temperature during any phase change. Label which phases are present in each portion of the curve. I do remember a lot of people just didn't read that direction. They just went into automatic mode last year. Calculate the amount of energy needed to do what it says. The graph, the directions say you have to do it and label it, but it's done for your own good. The reason we do these graphs like this is because it helps us plot how we are going to do this problem, and specifically how many steps it's going to take, and we can figure out what to do at each step. A 5-gram sample of steam at 115 Celsius. So 115 is the hottest I need. And this is degrees Celsius. And it's going to be changed to ice at -5. So -5 is the coldest I need. I don't have to have this really to scale, but I can go kind of close. There's 2 important numbers along the way. If you really take some steam and cool it off, when it gets to 100, it's going to condense because we've taken away enough for the heat of vaporization. When it gets to 0, it's going to freeze. So what's it going to do? A 5-gram sample of steam at 115 is changed to ice. So first it's got to cool to 100, condense, cool to 0, freeze, cool to -5. Key here is, okay, label which phases are present in each portion of the curve. It's going to get a little tedious, but this is phase. My phases are simply solid, liquid, gas. They're not my phases. They're just the ones. Somebody may talk about something called plasma, but that's like this high sun star sort of thing. And so that's not really our 3 phases: solids, liquids, and gases. So it's going to start as a gas. As it's condensing, there'll be a little bit of gas. There'll be a little bit of, so what's it really going to be? As it condenses, it might not look like it, but it's really going to be a liquid. It will start to settle on the sides of the container. Once it all condenses, it's now all liquid, and then it can finally cool off. Once it gets down here, it starts to freeze. We're going to have ice, but I'm going to write that as solid. Ice isn't a phase. It's a substance. Solid is a phase, solid, liquid, and gas. What else is going to be in there? Until it's all frozen, there will also be liquid. Finally, this will all be solid at the bottom. So thus far, I've drew this, I've labeled which phases are present, and I made sure that I had 2 for this one and 2 for this one. Here's what this tells me then. This is a 1, 2, 3, 4, 5-step problem where we have to add it all together. These 5 steps all together, we have to calculate. How much heat does it take to do number 1? How much for 2? When we get those 5 numbers, we add them all together. Really easy to make a simple mistake. Showing your work and documenting lets me give you most of the points if you make one simple little calculator error, which we all do. I probably will too. So it's a 5-step problem. So here's what I like to do. I like to just key on this. Well, it's 5 grams. Every single time, we're going to have 5 grams, 5 grams, 5 grams, 5 grams, 5 grams. There's 5 steps, and they're all dealing with 5 grams. The difference is I've got to start looking at number 1 and 3 and 5. I'm sorry. Number 1, 3, and 5. All of those have a slope or a change in temperature. All of those ones, I'm going to be using the m times c times delta t. You don't have to write it like this. I'm trying to help people understand it. If this helps you find success, you might want to write it like that. How do you know which ones are MC delta T? They have a slope, they have a slope, they have a slope. All the plateaus, all the plateaus are different. That's where there's a phase change happening. You couldn't use MC delta T because there is no change in temperature. You'd just get 0, so you wouldn't get any reasonable number. So there's a phase change happening. At number 2, what phase change? That is condensing. But if I really went back to my notes, I bet you I can't find the notes from the other day. But that condensing, we key on something called the heat of vaporization. Strange, because we're cooling it off. It's not vaporizing. It's the opposite of vaporizing. But that unit called the heat of vaporization is the amount of heat that you need to add to make it vaporize or subtract to make it condense. Same token down here on number 4. That's where it's freezing, the heat of freezing. But they don't call it the heat of freezing. They call it the heat of fusion. Okay, so far I'm just setting things up, and I've got a plan. It's a 5-step process. The first one is M times C times delta T. Well, at number 1, it's a gas. The specific heat, which is C, of a gas is 2.1 joules per grams times degrees Celsius. Change in temp, you got to be careful. Please don't take 115 and -5 and subtract them and think that's your change in temp. For number 1, it only changes by 15 degrees until something else happens. Well, I've got that all set up. Just go systematic and just keep going 1, 2, 3, 4, 5. Sounds good. How much heat does it take? How much do you have to take away to vaporize a sample of water, which is steam? It's a big number. It's 2260 joules per gram. And we have 5 grams. So 5 grams times 2260. That's going to equal something. You know what? I'm going to put my equal sign out here so that I have a big old line of them. Step 3 is a liquid. When the liquid's changing, it's going to change. Well, first of all, it's a liquid. So the C on the liquid is going to be 4.18 joules per gram degree Celsius. The change in temp is only from this point down to this point, which is a change of 100 degrees Celsius. Heat of fusion. How much heat do you have to take away to freeze a gram of ice? That's the one that's 334 joules per gram. No change in temperature because, well, that would be 0, and that's not how we do those ones. Finally, the last one. We're dealing with ice. It's still getting colder. Ice changes by 2.1 joules per gram times degrees Celsius. It takes 2.1 joules of energy to heat up a gram of ice by a degree Celsius. Now, the way of putting that is you have to take away 2.1 joules of energy to change the temperature of 1 gram of ice, make it 1 degree Celsius colder. How cold is it going to be? -5. 0 to -5 is a change of 5. Don't put the negative sign. We just want to know how much it changed, a change in temp. This is where it'll get a little tedious. I have to put my calculator up here. 5 times 2.1 . That does not seem right. So I'm doing a little mental math. 5 times 2 is 10. Yeah, it does make sense. 157.5 joules. I could go crossing out some stuff. I'm going to keep in a little bit faster mode. The next one, also 5 times 2260. 11,300 joules. The third section, 5 times 4.18 times 100, 2,090. The fourth one, the freezing section, 5 times 334 equals 1,670 joules. And the fifth one, 5 times 2.1 times 5. 52.5. I have to add those all correctly. 157.5 plus 11,300 plus 2090 plus 1670 plus 52.5. 15,270. Let me see if that Reality check seems right. It does. 15,270 joules. A lot of possible points on here, considering I had to show a lot of work. I had to make a graph with numbers labeled and label all those things. So I don't know how many points that's worth, but it's a pretty hefty one. Same song, second verse, but this is good because we're going to see that everything isn't a 5-step problem. We don't always start with steam and end at ice, or start with ice and end at steam. This time, we're starting with ice, but it's going to end at, uh-oh, it doesn't tell us. We're going to have to use our brain to figure out what 37 degrees Celsius is. So highest it's going to get is 37. I'm going to put it up there. It doesn't matter. I don't have to have this all the way up to 100 or more. The coldest it is doesn't tell us. Well, it was ice. What temperature is ice at? Sounds like 0 degrees Celsius to me. So here you got a hunk of ice, 75 grams at 0 degrees Celsius. And if you're going to melt it, then you have to add heat. Once you start adding heat, guess what it does? It just sits there at 0 while it melts until it finally melts, and then it can go up in temperature. I have 1, 2 sections. Now, the directions on the other side really still apply. This was solid. This is and liquid because it's melting. It started off as solid, but as soon as we start adding heat, there's some little bit of liquid. This is simply liquid. Kind of goofed that one out. Let me talk through that again. I have a flat line that'll have solid and liquid. And then once it all melts, it's all liquid. It's a 2-step problem. Should go quick. Both of them are 75 grams to start with. The first section is a plateau. It's the freezing. How much heat does it take to freeze? That's called heat of fusion. Look it up in your notes. Heat of fusion is 334 joules per grams times degrees Celsius. The next one is a slope. Every slope is an m times c times delta t. What do you use for c? Well, it depends. Do you have a solid, a liquid, or a gas? I happen to have a liquid. The liquid's specific heat of water is 4.18 joules per grams times degrees Celsius. Not all liquids are 4.18. Liquid water is 4.18. How much is it going to change before it's done? Well, it started, once it melted, it was at 0, and it changed to 37. That's a change of 37 degrees Celsius. So 75 times 334, 25,050. That's going to be joules. Why? Because grams and grams cross off. So this it's okay. I put the wrong unit there. 334 joules per gram shouldn't have the degrees Celsius. I was just in fast mode. I wouldn't mark that wrong on a test or something. I wouldn't even try to catch that. I'm looking for the big picture of setting things up neat enough so that I can see that you know what you're doing, and then documenting with enough, so you can show your labels. But if you goof a label up along the way in the work, it's not like I'm going to cue on that and mark a point off. 75 times 4.18 times 37, 11,599.5, 11,599.5 joules. Wow, this seems like a lot. I don't know why. Probably because it's so many grams. The last one was only a 5-gram sample, so that it makes sense that it would be about 15 times bigger of numbers. 25,050 plus 11,599.5 equals 36,649.5. 36,649.5 joules. We could be doing things in calories. I think we're just gonna we're not going to worry too much about that. If you can deal with units of joules, you certainly can with calories. They're just different numbers. We're not going to write this. I'm just going to explain the difference between what is happening at B and what is C. Specifically, this is just like the whiteboard activity the other day, keying on thermal and phase energy for each one. So at letter B, heat is being added, and that heat is just changing the thermal energy by increasing its temperature. The phase change is going to be the same all throughout B because it's not changing phase. When we get to letter C, all the energy that goes in is not changing the thermal energy. It remains at the same temperature. The phase energy is increasing, even though the graph doesn't show it. The graph's showing temp. It doesn't show phase energy. But we have to understand that the phase energy is increasing because it's evaporating. How do we know it's evaporating and not? Because let's think this through. What might the test be? The test could have been something like this. C, B, A. And I could do the same thing, but we're going to have to change that sort of thing around. This time when we discuss, we'll talk about less phase energy and less at C and less thermal energy at B. So consider whether it's a heating or cooling if over time the temperature goes down or temperature goes up. That's it for the practice test. Good luck.